Hi everyone, I am presenting a new rank-based causal discovery method for post-nonlinear causal models, which is a joint work with David Stride and Matthias Dortan from TUM. Learning causal relationships among complex systems is a central task in science. For instance, causal structure learning algorithms are being used to infer protein signaling networks from single-cell data. The gold standard for causal structure learning is to perform controlled experiments. However, it can be costly and unethical. So, causal discovery addresses the task of estimating causal structure from observational data. Structure equation models are a common tool for this task, which postulate noisy functional relationships between causes and effects. However, in their general form, they are not identifiable from observational data, and thus researchers focus on restricted subclasses of SEMs. Post-nonlinear causal models constitute one of the most flexible subclasses of SEMs that ensure unique identification from observational data. Existing methods learn functional relations by minimizing residual dependencies and subsequently testing independence from residuals to determine causal orientations. However, using independence criteria twice potentially leads to overfitting and makes them difficult to tune in practice. We propose a new approach that uses rank-based methods to estimate the functional parameters and exploits natural rank invariances of PNL models to disentangle the estimation of nonlinear functions from the independence test used to find causal orientations. We prove consistency in theory under some technical conditions and validate results on simulated data. Post-nonlinear causal models are a subclass of SEMs that formulate complex functional relationships between interacting variables. The causal perspective stems from viewing those equations as making assignments. The variable on the left-hand side, the effect, is assigned its value based on variables on the right-hand side. The causes via the following functional relations. First, the causes are transformed using arbitrary function gk, and an independent noise term is added. The final transformation is to apply a nonlinear transformation function fk, which is assumed to be strictly increasing and continuous. This includes the popular additive noise models, with fk being the identity function. In order to simplify the theoretical analysis, we focus on linear function gk. However, the method can be extended to arbitrary function gk using splines or multilayer perceptrons. The causal structure of PNLs is naturally represented by a DAG, and we aim to estimate the corresponding causal ordering based on an observational data alone. The last part of the slide is an example of PNL model with 4 nodes. In order to estimate functional relations in PNL models, the key observation is that every sinc node follows a PNL regression model given all the remaining nodes. Since the function fk is strictly increasing and continuous, it's invertible and preserves the ranks of its arguments. The main idea is to leverage this rank invariance to estimate the functional relations. We note that since fk preserves the ranks, we don't need concrete knowledge of fk to estimate beta if we use rank-based methods. We propose to maximize the pairwise rank likelihood by using that in PNL regression models, the probability of one sample being larger than the other depends solely on the distribution of noise, the remaining variables, and beta. We consider 2 cases here, when the distribution of noise is Gaussian and the general case with unknown noise distribution. In the first case, the linear transformation beta k and nonlinear transformation fk can be learned in a computationally efficient way based on ranks. In the general case with unknown noise distribution, we use smoothing to estimate the parameters. After estimating the linear transformation beta k based on the rank likelihoods, we use the following smoothed rank correlation objective function to estimate increasing function fk. The idea is to use rank invariances of the strictly increasing transformation to maximize an objective function that is close to the rank likelihood. The proposed method consistently estimates the functional parameters under some technical conditions. For more details on the assumptions, we refer to the paper. We can use the proposed rank regression method in typical structure learning algorithm that recursively identifies sync nodes. Here, the key idea is to leverage the independence of the noise variables. As mentioned before, sync nodes follow a PNL regression model. Thus, when regressing a sync node on all the remaining nodes, the residual is independent of all other variables. However, if a node is not a sync node, then regressing on the remaining variables includes at least one child of the node, which is thus not independent of the residual. Therefore, recursive sync node identification proceeds as follows. For each variable xk, we learn the functional relations with our introduced rank-based estimators according to the PNL regression model based on all remaining nodes. Then we use our estimates to obtain the estimates of the residuals and test for independence between our estimated residual and the remaining variables. Here we used HSIG independence criterion. However, in practice, any consistent independence criterion can be used. The one which produces the least dependence between estimated residuals and the remaining node is estimated as a sync node. After estimating a sync node, we remove it from the nodes and recursively repeat the same procedure to estimate causal order P. In the paper, we also provide a consistency result for this suggested method. Under some additional identifiability conditions, if the sample size goes to infinity, the estimated causal order is one of the possible valid causal orderings with probability 1. Further, we analyzed the performance of our method with synthetic data. For that, we generated data according to PNL models for randomly selected causal graphs under some different noise distributions. Additionally, we considered strong and weak signal-to-noise ratio settings. As a measure of error for an estimated causal ordering, we report the number of wrongly oriented edges in the complete graph corresponding to the estimated causal ordering. This is the number of edges in the true causal graph that contradict the estimated causal order. We compare our methods, the Gaussian noise method rank G, the general method for unknown noise distributions rank S, with two existing methods ABPNL and RESIT, which are also based on recursive sync node identification procedures. However, they employ independence criteria for both steps, learning and testing. In the plot, we compare these methods for graphs with 4 nodes with strong and weak SNR settings. We see that rank S method outperforms others except for rank G in weak SNR settings. For larger sample sizes, we compare rank G, ABPNL, and RESIT methods for causal graphs with 4 and 7 nodes. Rank G method is computationally efficient with computation times comparable with ABPNL method and outperforms the competition in all settings. Especially in the low SNR case, the rank G method outperforms significantly better and recovers a valid causal ordering even for smaller sample sizes. This is not surprising, since higher noise compared to signal strength induces more rank changes that propagate through the graph and thus better performance in weak signal settings. Moreover, in the experiments we see that it shows some robustness to the misspecification of the noise variables and even removes a valid ordering in the considered non-Gaussian settings. To conclude and summarize, we introduced a new structured learning algorithm for the flexible and identifiable model class of post-nonlinear models. Our method is based on ranks and thus recovers the overfitting problems of existing methods. By disentangling the learning and testing part of the recursive sync node identification, we show that our method consistently estimates a valid causal order under identifiability conditions, and simulation results validate this with good performance even in low sample sizes. Please feel free to contact us at any time or speak to us in a poster session number 3. Thank you.